In the previous video, we showed that the function in one of the previous videos that the function set 1x x squared or x squared x cubed, some triple of polynomials, are linearly independent because the Wronskian is not 0. Just recap that. Let's try this again. The Wronskian is going to be 1x x squared. The second term is going to be 0, 1, 2x, and the third term is going to be 0, 0, 2. So it would be madness if you chose anything other than the bottom row for expansion. So let's try that. Plus, minus, plus. Expanding about the bottom row, because there's only one term to consider here. It's 2 times 1 minus 0. And that's 2, which is clearly not equal to 0. So the Wronskian is not 0. It's linearly independent. And once you have linear independence, you can then go about figuring out an orthonormal basis for this. Please don't start doing this without first verifying that you have a linearly independent set. Otherwise, you'll be treading on very thin ice. So the procedure, the arbitrary procedure, it's a 3-step procedure. It is, first of all, you establish that it's a linearly independent set. And then once you have that, you can make one of them your initial, the seed vector. So it's usual to take the simplest thing to be a seed. So let's take E naught to be equal to the first function. I'm going to call this F naught, F1, and F2. So it's going to be F naught. In general, it's going to be any number of them. So E naught is going to be F naught divided by the magnitude of F naught. The magnitude of F naught is defined in the sense of the inner product space. So it's going to be the dot product of F naught with itself in the function space sense. Now in function spaces, the inner product of one function f with another function g is going to be the integral from a to b. And here I just want to not scare you really, but you take the complex conjugate of the first one times g dx. The reason for this is in quantum mechanics you will be required to do this. In the real space, f star or f conjugate is just f, so you don't really care. You just multiply the two functions, integrate them over all the range. So I should probably indicate the range here. I want to orthonormalize this on R, on the entire real line. If I don't want to do it on the entire real line, then actually, you know what? It's a bad idea to do it on the entire real line, I just realized. So let's try it on the interval -1 to 1. On the entire real line, the norm is infinite. So let's just restrict ourselves to a finite interval and see if we can find an orthonormal set in that finite interval. Okay, so with all that, let's do the second step. The second step is to form in a recursive sequence fi tilde. Fi tilde by definition is fi minus the sum of j less than I of ej tilde fi ej, I call it tilde, but it's caret, ej caret. So first I form E naught, then I form E1. E1 is formed by taking, first finding F1 tilde. F1 tilde is F1 minus, so let me just apply this process for F1 just to show you how it works. F1 will be F1 minus, there's only one term because there's only one term less than 1. So that's going to be E naught, F1, E naught. And then I'll find E1 by taking F1 tilde and dividing it by the norm of F1 tilde found in this fashion, where the norm itself, where the inner product itself is defined like that. This is called the inner product. Of functions. and that's called the norm or length of a function. So these are all extensions of concepts that you already have for vectors, except in function spaces. And once you have E1, then you go and find F2 like that next, and then you find E2, and you keep doing this over and over again. Proceed until all E0 up to En are determined. So this is the famous Gram-Schmidt process. It's more often used in function spaces than it is in vector spaces. That is probably why when you studied linear algebra as a standalone course, the instructor probably skipped Gram-Schmidt to save some time. Anyhow, let's now find out the orthonormal set of 1x and x squared. So in this case, f0 equals 1, f1 equals x, and f2 equals x squared. We're going to systematically apply the algorithm above to this. Let's find out what E1 is first, E0 is first. Well, I have to first find then what the length of the function f1 is. You may think, oh, the length is just 1. Be careful, it's not 1. You have to do the integral. So the length squared, which is, remember the length is f0 to the power half. So the length squared would be just f0. So the length squared is the integral from -1 to 1 of f0 squared dx. Well, f0 squared is just 1 squared, so that's just dx, which is just x between the limits -1 and 1, and that's 2. So this tells me actually that the length of the function f0 is √2. So I have my first vector E0. The first vector is f0 divided by the length of the function f0, and so that's going to be 1 over √2. Let's make a list and box it whenever we get a result. Hopefully the space is enough for all three, because as you will find out, it rapidly balloons in complexity, this method. So a lot of paper is advised. So now let's form f1 tilde. f1 tilde by definition is f1 minus the inner product of E0 with f1 times E0. So let's follow the instructions to the letter. f1 is x. The inner product means integral -1 to 1 of E0, which is 1 over √2, times f1, which is x, dx, times E0, which is another 1 over √2. So the 1 over √2's combine to give me half. So I get x minus half, integral x dx, which fortunately is easy, x squared over 2, between -1 and 1. And let's see, that's going to be at x equals -1 and 1, these will have the same values. So this will still be just x, because it's an even function evaluated between odd limits. So if you look at the graph of this function, it's this could have just been guessed immediately. If you look at the graph of this function, it's going to look like this, and you're evaluating it between -1 and +1, so you're going to have this negative area cancel the positive area, so the answer is going to be 0 for this integral. So you'll just get x. So aren't we lucky? The function f1 tilde is just f1 itself. Now what about the norm? Maybe things are not so good there. The norm of f1 squared is now going to be the integral -1 to 1 of x squared dx, which is x cubed over 3. Still not bad, -1 to 1, or 2/3. So if I divide the, I get E1 let me save some space here by writing it here. E1 is equal to F1 tilde divided by the magnitude of F1 tilde, and so that's going to be x over, don't forget to find F1 all by itself, F1 tilde all by itself, I have to take the square root. So it's x divided by the square root of 2/3, or written more simply, it's root 3/2 x. All right, now we are ready to find the bad boy, which is F2. F2 tilde, by definition, is going to be F2 minus all the projections of F2 along the previous vector directions. So subtracting out those components and leaving you with a purely orthogonal complement to the previous directions. So that's really what's happening here. Let's substitute everything. That's x squared minus, that's the integral from -1 to 1. F2 is x squared. E naught was that. So that's going to be 1 over root 2 dx. Always remember the measure. In this case, it's dx. E naught is again 1 over root 2 minus the next term. F2, which is x squared, times E1. Well, E1 is the square root of 3/2 x dx, and then square root of 3/2 x. So you can see this recursive procedure is really meant for the computer. And for higher number of variables, polynomials, you definitely have to write a computer program to do this. And that generates the so-called Legendre polynomials, by the way. So when you do this, the half and a half, 1 over root 2 and 1 over root 2 gives me half. That's x squared dx, which is x cubed over 3, between -1 and 1, minus 3/2 x. That's the 3/2 comes from root 3 over 2 and root 3 over 2. And the x is the one that's outside. And then you integrate x to the power cubed, which is x to the 4 over 4, between -1 and 1. So I won't waste any video time evaluating these things in great detail. I'll just tell you the answer. So that's going to be 3x squared minus 1 over 3. And you can look at the notes, but the evaluation of F2 squared, it's not terribly hard. It's just going to be a lot of writing. So it's 3x squared minus 1 over 3 squared dx. Now, if you're sensible, you'll stick this into Wolfram alpha and you'll get the answer. So that answer will turn out to be 1 over 3 root 8 over 5. And once you have that, you can form your last orthogonal vector, which is E2, as F2 tilde divided by the norm of F2 tilde. And that's going to be x squared. Sorry, F2 is this one. 3x squared minus 1. So you see F2 is a little different than x squared. Times 1 over 3 root 8 over 5. So that 3 cancels out, and I'm left with my last member of the orthogonal set, which is E2 caret square root of 5 over 8, 3x squared minus 1. So not to intimidate you, but the EI got this way are called the Legendre polynomials. Later in the course, we'll find that Legendre polynomials are really important in almost all aspects of science and engineering, and you can expand several problems such as heat conduction problems and Schrodinger equation problems, any kind of diffusion problems, in bases which involve these polynomials.